Question 1. The product is extracellular. For this reason, any method of cell disruption is not needed. Unit operation for this downstream process must be applied for industrial purposes. This means that unit operations must be easy to scale up. To concentrate the product, a series of filtration and microfiltration are proposed for eliminating the most abundant components and the easiest ones, following the main principles of any bioseparation. In each step of the process, a protein quantification assay and quantification of the antibody must be done for calculating the purity factor and yields for general evaluation for this downstream proposal. After this, it's recommended to do a 2D page to identify the properties of the antibody and the contaminants. With that, an ion exchange chromatography could be done using a membrane to make use of another property for having a more flexible process. The main purpose of this chromatography would be removing the contaminants. For that, the operational pH must be one that allows the antibody to not having any interaction with the membrane. In the non-binding proteins fraction, we will find the antibody, avoiding the contamination that the elution buffer does. Thus, to obtain the required purity, an affinity chromatography must be done. The antibody will be recovered in the elution fraction. Finally, for eliminating the elution buffer and to ensure the biosafety of the product, a tangential flow ultrafiltration must be done. In the retainted, we will have the product of interest, and this current will recirculate until the antibody reaches the desirable concentration. Question 2. For making a quantification of the column size required for the purification of a specific quantity of antibody, it is necessary to know the DBC at 10% divided by the total amount of protein to be processed. That will give us the necessary volume of the membrane for processing that quantity of protein. With this, we can obtain the size of the column. However, for calculating the size of the column, productivity also is important to consider. For that, the maximum flow rate that the column will support and the residence time must be considered. For scaling a column of chromatography, it is important to consider that to increase the size of the column, you cannot modify the length because this would change the residence time of the process. For that, the part of the column that could be modified is just the diameter. Increasing the diameter will increase the total volume column and the capacity for processing the new desirable amount of protein. Exact calculus is done by knowing the scale factor, which is a relation to the first flow, the one that we have in the smallest column, could be volumetric or mass flow of the interest of a product per unit of the time, divided by the volume of the column. This will be equal to the new desirable flow divided by the new volume column. The volume also could be expressed as P times a diameter squared divided by 4 times the length of the column. With that relation, we can clear the new diameter and make substitutions with data that we have for obtaining the new size of the column, keeping the length but increasing the diameter.